So welcome back to our discussion on kinematics. So in last class we got introduced to the idea of streamlines. So we saw that if I want to describe a flow field at a given instant in time, so the description of the velocity field at a given instant of time, this is obtained via streamlines. So we did a set of few problems yesterday. I'll just do few more and then get on to doing the description that we get from Pathlines, because it will introduce naturally what we think of the flow field. So we saw one problem yesterday where the x component was of velocity was x and the y component was minus y. So when we worked out the pathline equation, so dx, sorry, we had d minus x2 is what I'm using. So dx1 by u1, dx2 by u2, and then we got dx1 by x1 is minus dx2 by x2, and the final answer was a family of rectangular hyperbolas. So we got this in the previous class. We'll take another example. So the x component right now is x2 and the y component is minus of x1. So once again, to sketch the streamlines, we write down the equation for streamline. So u1 is x2 and u2 is right now x1. So if we write this out and integrate, I have x1 square by 2 is equal to minus x2 square by 2 plus some constant, which tells us that x1 square plus x2 square is a constant. So now we have a family of streamlines which are concentric circles. And when you draw streamlines, it's important that you also indicate the direction in which the motion is occurring. Because if you see, if I had a velocity field which was u1 equals minus x2, u2 is equal to plus x1, you would get the same sense of the same equation for streamlines. If you do the integration, the equation of streamlines are identical. So here, if I consider the case that is on top, then u1 is equal to x2, which means at this particular point, which is along the x2 axis, so this is x2 and this is x1, u1 is pointed in the positive direction. So u1 is equal to x2, and on this particular axis, it is pointing in the downward direction, which means the velocity vector at any point indicates the circle where you are traversing the circle in the clockwise sense. Okay. So this, and obviously you can see that if you take the case which is in the bottom, in this particular case, the velocity at along the x2 axis, which is where x1 is equal to 0, the velocity is minus x2, so it points to the left, and then if you were on the x1 axis, the u2 velocity would be top. So in which case, you would actually have a motion that is going in the counterclockwise sense. So even though the two have the same family of streamlines in terms of its mathematical form, it's important to indicate what are the directions of motion along the streamline. So drawing arrows on the streamlines is important. Let's take one last example for streamline, because we are going to use these families very soon. So, u1 is equal to x2 just like what I had, but u2 is equal to 0. So, there is only a single component of velocity which is along the x direction, and that velocity varies along the x2 coordinate. So, if I draw x1 and x2, now if you write down your equation of dx1 by u1 is equal to dx2 by u2, you can see that dx2, which is u2 by u1 times dx1, this is equal to 0, because your u2 is equal to 0, which means that x2 is equal to a constant is the equation for streamline. Now, what is x2 equal to a constant? All lines that are horizontal or parallel to the x1 axis, those are streamlines. Direction, it's going from left to right. Okay. Later we will see, I have indicated the arrows here to indicate the direction, but if I were to indicate the magnitude of the velocity gets higher as you move away from the origin. So, if you were to indicate this arrow as the magnitude of the velocity, then the arrows are going to basically become shorter and shorter as you go towards the origin, or in a sense that if the velocity is going to increase as you go up. But in the context of streamlines, you have streamlines which are parallel. They are parallel to the x1 axis, they are horizontal streamlines. So, now the question we could ask, let us stick to this particular problem itself, that if I release a fluid particle, so I choose a particular point, going back to the descriptions that we learned, Eulerian and Lagrangian. So, if I were to release a fluid particle at this particular point, mark this point with as coordinate A, with the position vector A, what would that fluid particle do? How would it move? Now, this becomes a question of finding the solution to the equation dx1 dt is equal to u1, dx2 dt is equal to u3, and if there was a third component of velocity, dx3 dt is u3. And as you realize, for a general problem, this is a function of all the three spatial coordinates as well as time. So, now if I have to solve a problem which is an initial value problem, given that I was at a particular point at t equals 0. So, I have started my clock, a fluid particle was labeled and tagged at the point A, where would it be at a later instant of time? So, to answer this question, this is what we need to do, and let us do that systematically for the velocity fields that we have chosen. So, let us consider once again the velocity field u1 equals x1 and u2 is equal to minus x2, and we are going to do most of these problems sticking to two-dimensional flow fields. The extension to 3D algebraically can become more tedious, but the ideas remain more or less the same. So, now if you write this equation out, dx1 dt is equal to x1, which means if you integrate this equation, x1 of t is x1 at t equals 0 exponential of time t. It's a straightforward first order differential equation, linear in the dependent variable x1. So, here x1 is a dependent variable, it is the coordinate that you are trying to calculate for. So, this is why I am trying to bring in the idea we learned regarding Eulerian and Lagrangian. So, here you are tracking a fluid particle which started off from some initial position at t equals 0 and evolved due to this flow field. So, this flow field is given to you. In this case, the flow field is x component is proportional or equal to x1 and the second component is equal to minus x2. So, if you now solve for the second coordinate, dx2 dt is equal to minus x2. So, x2 of t is x2 of 0 or exponential of minus t. Now, we have solved what the coordinates are, But going back to the previous point that we had, if it starts off from this blue dot, where would it actually be? Now, this velocity field that I have chosen is a steady velocity field, which means that the streamline pattern doesn't change with time. This is going to be the streamline pattern at t equals 0, at some dimensional units 1, dimensional units 10, or a dimensional units a million, right? So, it doesn't matter what time units you are looking at, what time values that you are choosing, your velocity field and the corresponding streamline, they remain completely unaltered. There is no change. So, as this fluid parcel moves at immediately the next time instant, so it starts off at a at t equals 0, at immediately the next time instant, it has moved a little bit. Let's consider a time increment delta t, and it would have come to a point on this particular curve, and it realizes that the velocity hasn't changed in time. The velocity was what it was exactly before that. So, if I argue from the point of view of streamline, because as it moves to the next point, and the velocity at that particular point is exactly the tangent to the curve where it is. So, every time it makes a step, it continues to lie on that particular curve. So, the streamline pattern gives us a clue that if the streamlines do not change, and if I start on a particular streamline, I cannot move away from that streamline. Because the definition of streamline is that the velocity vector is always tangential to the streamline. Or a trivial statement, or the trivial corollary would be that the normal velocity to a streamline is 0. That at any point on a streamline, if I write the tangential and normal component, the normal component is 0 and the tangential component is the magnitude of the velocity. There is no normal component to the streamline. So, if the streamlines do not change, and as I move along the streamline, I realize that at every point on the streamline, I am constrained to move along the streamline because I don't experience any normal component of velocity. So, from the streamline picture, if the flow is steady, I should be deviating from that particular streamline. If I start on a particular streamline, I stick to that streamline forever. This is based on the definition of streamline. Now, if I am integrating these equations and finding the trajectory of the fluid particle, is that in agreement with what I just said? It should be, because now what we are trying to do is we are trying to actually show that where would a fluid particle be if it starts off from some position as a function of time, as I integrate as a march in time. So, there should be an agreement, otherwise we are violating the previous conclusion. There should be an agreement that the trajectory should also coincide with the streamline, because the underlying flow field is steady. So, let us try to confirm that. So, I have these two coordinates, there is an explicit time dependence. So, it is not obvious that it is indeed a streamline. So, to make this obvious, what we will do is we will try to write down the equation by eliminating time. So, in this is quite easy, the elimination, because I have an exponential of t, and in the second equation I also have an exponential of t. So, in the first equation I have an exponential of t, in the second equation x2 of t is equal to x2 of 0 exponential of minus t. But from the first equation, exponential of minus t is x1 of 0 by x1 of t. That is another way of writing the time variable. So, if I plug it here, I have x2 of 0 times x1 of 0 by x1 of t. So, that tells us that the coordinate at any point in x1 and x2, the product, is equal to where it started out from. Now, go back to the streamline equation that we derived. We had x1, x2 is equal to a constant. So, this gives us an important conclusion, and this is not just a stroke of luck. So, these equations that we are solving for, the trajectory equation, these are known as path lines. They are the path taken by a fluid particle as it navigates the flow field. So, the important conclusion that we have for steady flows, streamlines and path lines will coincide. That's the important conclusion that we have. The converse statement for unsteady flows, streamlines and path lines may not coincide. Why did I say may not? Actually, a stronger version would be saying will rarely coincide. So, we saw an example in the end of last lecture. If I were to choose the velocity field as u1 x1 into t and u2 minus x2 of t, from the streamline equation, which is dx1 by x1t dx2 by minus x2t, I get back the same equation, x1 x2 is equal to a constant. From the path line equation, I have dx1 dt is equal to x1 of t, which has a solution that x1 of t is x1 of 0 exponential of t square by 2. dx2 dt is minus x2t, which has a solution x2 of t, x2 of 0 exponential of minus t square by 2. If you once again do that elimination that we just did, you again land up with an equation which is x2 of t, x1 of t is equal to x2 of 0, x1 of 0. So, even though this was an unsteady flow, the streamlines and path lines are coinciding. So, as the particle moves along that trajectory, it continues to remain on that particular streamline. But in general, this is a very special kind of a flow, where what I have done, I basically have the same time dependence in the two velocity components. One way to make this problem a steady problem, that you can define a new time, you can define a particular new time, and in that the flow becomes steady. But this is an exception. The general scenario, when you have an arbitrary time dependence in the problem, so when you have u1 arbitrarily dependent on time from what is the dependence for u2, you are not going to get streamlines and path lines coinciding. We will try one more, at least two more path line calculation for the steady problem to convince ourselves. So, we took an example which was u1 is equal to x2 and u2 is equal to minus x1. So, let us do the path line calculation. So, in path line calculation, the key difference that you are doing from your streamline calculation is that time is now an independent variable in path line calculation. In your streamline calculation, you are finding the streamline for a fixed value of t. So, even though you arrive at this conclusion that they are coinciding etc. for a steady flow, this is an important thing which should never be left behind. That when you do a streamline calculation, always consider time to be fixed. You are doing the streamline, you are finding the streamline pattern for a fixed instant of time. If the velocity field happened to be independent of time, then obviously it doesn't matter, time doesn't appear in your calculation. But when you are doing a path line calculation, you have to do an integration with respect to time. So, now I have a set of coupled first order linear ODEs. So, we can make some progress. So, instead of, because x1, the rate of change of x1 depends on x2 and x2 depends on x1. So, we can apply a trick and take a derivative once again of the first equation. So, we get dx2 dt, and then using the second equation we have x1. So, we have an equation which is something that would remind you of a simple harmonic oscillator. So, x1 is some constant A cos t plus some phase B. That is the general solution of this equation. You could write it also in terms of A cos t plus B sin t. I have just written it in terms of the two independent constants being A and B. Now, what about x2? x2 is dx1 dt, which means it is minus A sin t plus B. Now, what did we find for the streamlines for this problem? The streamlines for this particular problem was dx1 by x2 is equal to dx2 by minus x1, which gave us x1 square plus x2 square is equal to constant. So, we got a family of concentric circles. Now, here it still has a time dependence. So, whenever you do a path line calculation, your effort should be to see if you can eliminate time. So, one way for here to eliminate time is if I square the first equation and I square the second equation, add them up, time disappears from the picture and I get back the equation to be family of concentric circles, which it should be. It's just a confirmation of that statement. So, the path lines coincide with my streamlines. So, this is what you will continuously keep doing, that whenever you see a steady problem, your first conclusion is that streamlines and path lines should coincide. Now, the problems obviously that we have chosen to do in this exercise are simple enough that we can work it out using pen and paper. But in most problems that you will encounter in fluid mechanics, most problems will not have that luxury while you do it using pen and paper. So, in which case you would actually have to do a numerical integration of equations. So, you will have a set of, for an arbitrary three-dimensional problem, you will have a set of 3 differential equations, and as you have guessed maybe that I chose, for reasons of being able to solve here, problems where the velocity field depends linearly on the spatial coordinate. If the velocity field was a nonlinear function of spatial coordinate, I won't be able to generally do it analytically. So, a general velocity field will not be a linear function of spatial coordinate, may necessarily not always be steady, in which case the solution to this have to be a numerical solution. So, you will have to do a numerical integration of the ODEs, and by numerically integrating you will actually find what the path line is, which is typically what you do. You obtain your velocity field, either you know the velocity field from a simulation or you know the velocity field from experiments, or even in some cases the velocity field is analytically known, but the path line calculation would be numerical in nature. It would not be analytical in nature. So, this is the general approach of what you do for path line calculation. Now, let us take an unsteady problem and actually see the distinction that we have between streamlines and path lines. So, I will consider a flow which is once again two-dimensional, and to illustrate the difference I will have a time dependence in the u1 component, the u1 velocity field, whereas the u2 velocity field is steady, and I am emphasizing that this is flow is two-dimensional. So, I am not looking at the third component of velocity. So, let us do streamlines. So, streamlines require us to solve the equation dx1 u1 by u1 equals to dx2 u2, which says that I will need to have this as my equation. Now, again this we can do analytically. Ln x1, I will take the 1 plus t multiplies here, ln x2 plus a constant. So now, if you write this out, x1 raised to the power 1 plus t, I bring the logarithm to the other side, so is a constant, which gives me the streamline equation to be x2, x1 raised to the power 1 plus t. That's the equation for my streamline. And as you can see in all this calculation, I have done this for a particular instant of time. Time is there in the velocity field. The velocity field is not a steady velocity field. So if you plot the streamlines, let's consider the streamline at two separate instants of time, t equals to 0 and t equals to 1. So for t equals to 0, the streamline equations, there should be a constant here. I have missed. There is a x2 is equal to a constant times x1 raised to the power 1 plus t. So if t is equal to 0, I get x2 is equal to cx1. These are straight lines. So the streamline pattern are basically straight lines. And once again, as I said, it's useful to have the direction pointed out. So the velocity is outward in this case. At any point, if x1 and x2 were positive, both u1 and u2 would be positive. What about t equals 1? Now x2 becomes x2 is equal to c x1 square. So this now turns out to be quadratics. So I get functions right now which are quadratic functions. Once again, the flow is emanating from the origin in that first quadrant. But the important fact here is that you have the velocity field giving you a streamline pattern which is very different from what you had before. Right? So this automatically starts telling you that you are your streamline pattern is at a fixed instant of time, and you can see the difference. And you can keep doing this exercise as you keep going for higher and higher time. The velocity field is going to get increasingly steeper near the origin and blowing up faster. It will be a higher order polynomial. Good. So that was the effort to find the streamline for that particular problem. Let's do path lines for that same problem that we have. So u1 is x1 by 1 plus t, u2 is x2. So path line calculation is dx1 dt is equal to x1 divided by 1 plus t. Integrating requires us just to write them clubbing in terms of x1. So once again, this is a problem which we can study analytically. So ln x1 is ln 1 plus t plus a constant. Okay. So this, so let me not skip steps. So ln x1 divided by 1 plus t is equal to a constant, which means x1 is equal to, let's say, c1 1 plus t. Now c1, instead of writing it as c1, this is a path line, so I should write it as x1 of t, x1 of 0, 1 plus t. That's the path line equation for the x1 coordinate. For the x2 coordinate, dx2 dt is equal to x2, and this we have done just a while back. So x2 of t is x2 of 0 exponential of t. So now, as I said, in order to make sense of the path lines, if I want to plot the path lines, I would want to plot x2 as a function of x1. So to do that, let's try eliminating time from the equation for x1. So from there we have x1 of t divided by x1 of 0 minus 1. So when I plug that in, I have x2 of 0 exponential of x1 of t by x1 of 0 minus 1. So the path line equation that we have is x2 of t, x2 of 0 exponential of x1 of t by x1 of 0 minus 1. No resemblance whatsoever to our streamline equation that we got, which was of this particular form. So this is our streamlines at a given instant of time, whereas this is a path line equation given that it started off from the point x1 0, x2 0. So if you trace these curves out, here you have this exponential form, whereas here you have this power law form. So they are not going to coincide. There is no reason for them to coincide because this is an unsteady flow. There is absolutely no instance of it being coinciding. So to plot path lines, what you need to do, you choose a particular point. So let's say the point was 1, 1. So at t equals 0, I have a fluid particle that was at the location 1, 1. And then you ask the question, where would it be at a later instant of time? So this is x2 exponential of x1 minus 1. So this is a particle that at t equals 0 was located at 1, 1. So now you have at x1 equals 0, so as I move forward, it's going to be something like this, exponentially increasing. Whereas if you ask the question that what does the streamline look like for a fluid particle that is at 1, 1. Draw the streamlines passing through the point 1, 1 at different instants of time. So this is, let's just do one thing, make sure that we don't mix them up. So this is a path line that I have, which is x2 is equal to e to the power x1 minus 1. So that's my path line. Now let's try to draw streamlines that are passing through point 1, 1 at different instants of time. So here, if I am interested in finding out the streamline that passes through point 1, 1 at different instants. So let's say that at t equals 0, this is C2 equals constant times x1, which means if it has to pass through the point 1, 1, the constant should be 1. So I should have, my lines are not drawn to scale, but I should have a streamline which should look like a straight line. Then at the next instant of, let's say t equals 1, it is sum of x2 is equal to constant x1 square. Once again it will look like a function so the slopes are not really representative because the exponential will blow faster, but what would happen is for the streamlines it will start to look like this at different instants in time. So you are going forward in time, whereas the path line that you would have would be something that is going to blow up even faster as exponential in time to that point. So this is an example of what we do regarding path lines and streamlines. I'll do one more unsteady problem, which is a little bit more involved, but we will make some approximations and work with it. So u1 is a constant exponential of minus, okay, let me just choose kx2 sine kx1 minus omega t. u2 is minus a, let's just choose one sec, I'll just keep it a little simpler. So, a exponential of x2 sine x1 minus t, and u2 is minus a exponential of x2 cos x1 minus t. So, this is a very simple way of writing what is the velocity field due to waves that are there over a fluid. So, you have a fluid which has an undisturbed surface, this is air and water, and you have waves that are propagating on that surface of the fluid, and I have written down a caricature of what that velocity field is. I have gotten rid of few constants which will involve the wavelength of that wave and the frequency, but for the purpose of what we are trying to understand, let us just consider this particular velocity field. So, if you want to write down and solve this velocity field and find its streamlines, as you can already see that this is an unsteady problem. So, you will have dx1 by u1, which is the following sine x1 minus t, and this is x2, this is x1. So, I am basically looking below the x2 equals to 0 level, and then I have dx2 a exponential x2 cos x1 minus t. So, here then we have a form where dx1 cos x1 minus t by sine x1 minus t is minus dx2. So, x2 is going to be an integral of cotangent x1 minus t dx1, assuming t to be a constant. So, when you plot the streamlines are going to look something like this. At a given instant of time, the streamline pattern will resemble of this form. As you move in time, the streamlines are going to shift. They will have the pattern similar to this, but they are going to shift with the wave. So, you can do the calculation and get an analytical answer for this, but the broad story is that you will have a streamline pattern that looks like lines which will emanate from the top free surface and then go back to the free surface, and you will have these kind of semicircular cells which are going to move in one particular direction as you move in time. So, let us focus on the difference of path lines and streamlines. So, instead of the exact analytical calculation. Now, if you do path lines, I have dx1 dt is a constant x2 sine x1 minus t, and dx2 dt is minus a x2 cos x1 minus t. Now, as you can see, now we are in a soup because we have a set of nonlinear coupled differential equations. So, we can't solve this analytically. So, it's something for which we will have to do a numerical calculation. But we can do some small approximations to see if there is a first level calculation that we can get. So, what I will do is I will say that the particle has just started out from its initial position. So, I am looking at small deflections from its initial position. So, it was at x1 of 0, which is a constant. It is at some initial location x1 of 0. It is at some initial location x2 of 0, and I am looking at where the displacements from that initial position is not very large. And this formally can be argued based on how the amplitude of the wave etc. is. But if we just do this and substitute into our equation, so I had dx1 dt is a exponential x2 cos x1 minus t. What did I have? Sine, sorry. So, I had sine x1 minus t, whereas dx2 dt is minus a exponential of t cosine x1 minus t. So, if I make that assumption that x1 of t is x1 of 0, a constant delta x1 of t, where delta x1 of t, the magnitude is much smaller than x1 of 0, and the same applies for the second coordinate. Then d dt of delta x1 is a x2 of 0 sine x1 of 0 minus t. Now, this kind of an approximation, what it does, it reduces my nonlinear differential equation to a linear differential equation. It also removes the coupling because everything on the right hand side is purely a function of time. I've just substituted that all the coordinates on the right hand side x2 and x1 are replaced by its constant value, and the rate of change only depends on that small displacement from that constant value. So now if you integrate this equation delta x1, and we have been doing something like this, x2 of 0, I'll get cos x1 naught minus t. This is what I'm basically going to get as a solution with some constant that I have. So if I similarly solve for the other one, dd2 of delta x2 minus a x2 0 cos x2 0 minus t, if I integrate it just like the previous one, I will have a x2 0 sin x2 0 minus t, where x1 0 and x2 0, this should be x1 0, this should be x1 0. So now if you write dx delta x1 square, which is a function of time, delta x2, which is a function of time, and square it and write it, you are going to get a square exponential of 2 x2 0, because cosine square plus sine square would be 1. So what this tells us is that if I were looking at a fluid, even though the streamline pattern looks like this, a fluid particle is going to execute circular orbits. And the orbit basically, so the equation that we got is that delta x1 square plus delta x2 square is a square exponential of 2 x2 0. So about that point x1 and x2, it's doing this. So and the size of that orbit is going to get bigger as you go towards the free surface, and it is going to diminish as you go below. So the streamline and path line that we have, those streamline and path line calculations look quite different here. Now what I'll show you is this was a calculation that was done with the approximation for the numerical part. So let me just show you what would happen if you do the full calculation. So this is the full calculation. So you see the streamline pattern in the background, it's an unsteady problem, and you see the path lines are doing this orbit, but it is not fully closing. So the assumption that we made, that we have this small deflection, what that assumption did was it told us it makes this circular orbits, whereas in fact what it actually does, it tries to come back, but because the flow is getting weaker and weaker as you go down, there is an exponential of x2 0. x2 0 is negative, so as it goes down, the flow gets weaker. So on its backward trajectory, it doesn't really have as strong a flow as it had on the forward trajectory, so it doesn't close a loop and there is a drift that you get. So the Lagrangian picture is very different from what you get from the Eulerian picture, that's one thing. And the Lagrangian picture from the full numerical simulation is also very different from what you get from the first linear calculation. And this becomes quite important when you are thinking of particle transport by waves. So if you are interested in what wave field does, and you are thinking of this is just a single wave that you have, but in the ocean when you are thinking of transport of various kinds of things, active or passive, they are constantly being acted upon by waves. And what you are interested in when you say transport, you are interested in the Lagrangian transport, that how much does it actually move. And as you can see that a velocity field which we can quickly write down in class does offer this kind of a complexity. So that the first picture you can get the flow field analytically, the streamlines analytically. Path lines we can't get analytically, we can do an approximation and we get those circles, and you can see that the size of these orbits become weaker as you go down with depth. So that part is there. But the crucial part which the numerical calculation tells us is that it's going to not complete the orbit, but effectively have a slight displacement towards the direction of the wave. So that's the piece which is regarding what streamline pathline distinctions actually give us. So with that, I will stop here.